In this video, I'm going to explain the technical definition of definite integral. So the integral from a to b of f of x dx, what we're looking for is to find the area underneath this function and above that interval a to b. And there's a really technical definition that involves sums. So we have that the integral is equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of xk star times delta x. So that probably looks very confusing. So what does that mean? Okay, what does that definition mean? That's what this video is all about. So let's begin with a positive function f. So we'll deal with a situation where f is not a positive function at the end of the video. But let's suppose f is a positive function on a to b. So this means that the graph lies above the x-axis. Now let's divide the interval a to b into n equal subintervals. So let me draw some subintervals here. So this first interval here, let's label these points x1, x2, x3, and so on. And let's call b, that will be x sub n. So I guess n in this case is, let's see, 4, 5, 6, 7. N is 8 in this case, so b would really be x sub 8. I'm just going to call it x sub n. Okay, and a is really x sub 0. So label those points. The next thing we're going to do is within each of these sub-intervals here, we're going to pick a point. Okay, it doesn't matter which point. I'm just going to pick the midpoint here. It doesn't have to be the midpoint, but let's just do it that way for the time being. And let's call this point, well, we're in the 1, 2, 3rd subinterval, so let's call this x sub 3 star. So x sub 3 star is just a point inside that 3rd subinterval. And what we're going to do is we're going to make a rectangle above this 3rd subinterval. And the question is, how high should I make that rectangle? Well, at this point here, go up to the function value at that point, and we will draw our rectangle to have that height. Okay, and so what we're interested in is what is the area of this rectangle. In fact, we can do that for all of these rectangles. If we did it in the first one here, this point we would call x sub 1 star. It's a point in the first subinterval, and the height of it would be right here. Okay, now you can do this for all n of these subintervals. I guess there are 8 subintervals in this problem. But notice that if we do that, then the total areas of these rectangles, when we do all of them, if we add up those areas, it will approximate the area underneath the curve that we're looking for. It will not give us an exact answer, but it will give us a good approximation. Now, I made 8 subintervals. If I had only made 2 subintervals, so just chop this interval in half, let's say, then I just have these big boxy looking regions here, and we would not have a very good approximation of the area under the curve. Likely we would not. So what is really helpful to get a good approximation is to have lots and lots of intervals. Here I have 8, but if I had 100 intervals, we would have a better approximation, because notice we're off a little bit here, and we're off a little bit right here. Okay, we're not getting the exact answer, we're just getting the approximate area under the curve. Okay, so what do we get when we add up the areas of these rectangles? Well, let's call the width of one of these rectangles delta x. Okay, and I wanted them to be equal subintervals, so delta x is the same for all of these. And I guess if you want to get technical, delta x is equal to b minus a over n. b minus a is just the distance from a to b, and we're dividing it by n because we have n subintervals. Okay, so delta x is just that number. Okay, so what is the total area of these rectangles? Well, the total area of the rectangles would be equal to A1 plus, where A1 is the area of the first rectangle, plus A2, where A2 is the area of the second rectangle, and so on, all the way up until we get to the last rectangle, which has area A sub n. Okay, so what is A sub 1? Okay, what is A sub 1? What is the area of the first rectangle? Well, notice it will be the width of the rectangle times the height of the rectangle. Now, the width is delta x, and the height, what is the height? Well, it's this height right here, which is f of this number x sub 1 star. Okay, so the width is delta x, the height is f of x sub 1 star. So a sub 1 is f of x sub 1 star times delta x. Okay, that's a sub 1. Okay, a sub 2 would be f of x sub 2 star times delta x, and so on. Okay, until we get to the last one, f of x sub n star times delta x. Okay, now we can write this more compactly in summation notation. We're adding some things together, so we can sum this up. We can think of this as the sum from k equals 1 to n of f of x sub k star times delta x. Because notice if you plug in 1 for k, you get f of x sub 1 star times delta x. That's this term right here. When you plug in 2, you get this term. You plug in 3, you get the next one, and so on, till once you plug in n, you get this last term. Okay, so this sum here represents the total area of those rectangles. Now, if we want to find the exact area underneath the curve, what we would need to do is have a bigger n. We'd need to have more rectangles. So to get the exact area, what we can do is we can take the limit as n approaches infinity. Okay, so the exact area will not be this sum, but the limit as n approaches infinity of that sum. Okay, and so this will give us the exact area under the curve. Now, in fact, this is how we define the definite integral. Integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k star times delta x. That is our definition of definite integral. Okay, so the definite integral is a limit of sums. Now I want to point out a couple things about the notation here. Notice this integral symbol here and this limit of the sum. Okay, the sum signal is kind of a jagged thing here, but when we take the limit, it kind of smooths out and it becomes this integral symbol. Notice the delta x here kind of looks like the dx. Okay, and the f of x k star looks like just f of x. Okay, it turns into f of x. Okay, so sort of associate this with this, and this with this, and also the middle things together. Okay, that's one way to kind of think about it. Okay, now one last thing you might wonder is what if f is not positive? Okay, what if f is not a positive function? Okay, so suppose we have a function that maybe dips below the x-axis, okay, on our interval a to b. Okay, well again, we're going to chop up the interval into n subintervals. Oh, one thing I want to point out, if f is not positive, our definition of definite integral still stays the same. We still have the same definition even if f is not positive. Okay, but what does this give us if f is not positive? Well, if we look on one of these subintervals, so if we call this x1, x2, x3, x4, and so on, and let's call this point here x sub 1, 2, 3, we're in the fourth interval, x sub 4 star. If we draw, oops, make this a little farther here, draw the rectangle there, and we multiply delta x by f of x sub 4 star. Now notice f of x sub 4 star right here is this number. F of it gives us this negative number down here. So f of x sub 4 star is negative. Okay, f of x sub 4 star is negative. Okay, and so when we multiply it by delta x, we get a negative number. So even though the area of this rectangle, area is always positive, when we multiply f of x sub 4 star times delta x, we get the negative of this area. And the reason is because f of x sub 4 star is negative. Okay, so we still get this length times this length, but it's negative. So that's why the definite integral really gives you the net signed area. Okay, because these parts that are below the x-axis, they sort of count as negative. One last point I want to make about this definition is that we don't use it very often. Most times when we want to calculate the integral from a to b of f of x dx, we don't use the definition, we use a theorem how to calculate this. And that theorem is the fundamental theorem of calculus. The fundamental theorem of calculus says that a different way to compute this integral without using the definition, a different way to compute it is to find an antiderivative of f of x and then plug in b into that antiderivative, plug in a, and subtract them. So that in most practical situations, that's how we calculate this integral.